All right, so on to number 7 here. Excuse me. On to number 7 here. I know that we had kind of left off at this particular spot. So again, what we really are trying to concern ourselves with is knowing and understanding the indication of which type of curve we have. Let me go full screen here. Sorry. So again, we know that it's going to be a Rose curve, as we said. If we're multiplying all the way through, we know that it's going to be a limacon if we're adding or subtracting, finding some kind of a sum or difference in there. So more specifically, if it's a Rose curve, and I know that I'm kind of jumping all over the place, sorry, but if it's a Rose curve, we're also supposed to comment on the number of petals. So for instance, part B, we know that this is going to be a Rose curve. And again, I'm saying that because as you can see, there's no addition or subtraction. It's all multiplication all the way through. So for this particular problem, not that this plays into what we're trying to do here in number 7, but A is equal to 6, N is equal to 7. So A being 6, that's going to help us to determine the length of the petal on my Rose curve, but that's, again, not what we're being asked about. Instead, we're being asked about how many petals we're going to have. So since N is equal to 7, and 7 is an odd number, then we know that we're going to have 7 petals. Okay? So in a very similar way, jumping down to part D, this is also going to be a Rose curve. And if we're looking at the A and N values, A is going to be 3, which again is going to help us out in determining the length of the petal, again, which is great for our graphing and things of that nature, but since all we're supposed to do is comment on the type, all that we can get away with saying that it's a Rose curve, and since N is equal to 4, and it's going to be an even number, so I have to double it. 4 times 2, we can say this is going to have 8 petals. So for problems like these, that's really all that we need to know in terms of the Rose curves. As you can probably already tell, A and C, these are going to be limacons, and we need to comment on which type of limacon we're going to have. So as you're probably remembering, A and B, they're going to create a ratio, specifically A over B. And this is going to tell us, that ratio, I should say, is going to tell us specifically which type of limacon we have. So if A over B is less than 1, we know that this is going to be a limacon with the inner loop. Whereas if A over B is equal to 1, then that's going to lead to a cardioid. If A over B falls between, so like it's greater than 1 but less than 2, then we're going to say that we have the dimpled limacon. And if A over B happens to be, I'm going to switch this sign around, try to do this lazy way. If A over B happens to be greater than or equal to 2, that's when we're going to have the convex limacon. So that's those are the tells, I should say, as of right now. And when we're looking specifically at number 7A, we would say that here's A, here's B. So my A over B value, when we plug in, is going to be 1 over 4. So from that regard, if A over B is 1/4, then what that's going to allow us to do is to say that number 7, part A, limacon with an inner loop. So limacon with the inner loop. Again, we can say that confidently because of the fact that A over B is less than 1. So again, limacon, inner loop. Jumping down to part C. This time, remember, we always take absolute values. I feel like I did not mention that in part A because it was positive. But we would say that A is 8. We would say that B is 5. So from that standpoint, my A over B value, A over B is going to be 8/5. So 8/5, that's bigger than 1, but it's less than 2. So if A over B falls right there in that range between 1 and 2, again, we know that this is a limacon, and specifically it's the dimpled limacon. All right, so hopefully we're feeling pretty good about those. If you're sitting there scratching your head, thinking, well, what's the difference between addition and subtraction? What's the difference between the sine and the cosine? He didn't mention those at all. And that's because for these particular problems, it didn't matter. It's the next couple of problems that where we actually have to draw the graphs. That's where it's absolutely going to come into play. So for number 8 that we have here, hopefully we can just look at my given equation, r is equal to 4 sine of 3 theta, and realize that, yeah, this is going to be a Rose curve. Okay? So specifically when we're identifying the shape, just like we did on the previous slide, just to say it's a Rose curve isn't 100% good enough. If we also looked at the fact that A is 4 and N is 3, just like, again, just like previous slide, if N is an odd number, that tells us how many petals we have. So it's a rose curve with 3 petals, and we can go from there. The max R value, that's basically just restating what A is equivalent to. So max R value here is going to be 4. The number of zeros, we could get away with it. Now, there is a shortcut, remember. If this were a cosine problem, then the number of petals is equal to the number of zeros. But since it's a sine problem, we have to think number of petals plus 1. So 4 petals, whoa, I can't read apparently. 3 petals plus 1, we're going to have 4 zeros. All right, so picking up, again, have pause there for a moment. The specific zeros, we could do that now, but we're probably a little ways out. Pause again here. So, all right, sorry. Phone calls and stuff like that. All right, so back to this though. If we know that there are 3 petals, since it's a sine curve, that means that there's going to be 4 zeros. Because again, 3 petals plus 1 more gives us 4 zeros. So for these particular problems, again, where the hassle comes in, we have to think of it this way: that whether it's a sine problem or a cosine problem, we're still going to have to go through a little bit of hassle. And that hassle that I'm speaking of is this little formula that n theta is equal to pi over 2. So because this is a sine problem, that means, or that little equation, this is going to help us to determine where our first petal is located. Now, if this were simply a cosine problem, no big deal. On a cosine, first petal always goes on polar axis. So that's not what we have, though. So for this particular problem, we're going to have to solve for it. We've already established that n is equal to 3, so 3 theta is equal to pi over 2, multiplying both sides times 1/3. I know that theta is equivalent to pi over 6. So again, that's where my first petal is going to live. So on this pi over 6 line right here, I'm going to just label it pi over 6. We know that that's where my first petal is going to lie. We also know that the max R value is 4, so counting out 1, 2, 3, 4, I know that this is where my first petal is going to go. All right, so from here, the next crucial piece is my spacing. So I know that if we have 3 petals, we're going to space these 3 petals out, evenly. And I also know that if we're to consider degrees, in which you're not going to do this in degrees, but sometimes it's easier to think that way, that if we had 360 degrees in a full circle, divide that by 3 because I have 3 petals, that now every 120 degrees is where I put the petal. So with the exact same thought process in mind, if one full circle is 2 pi, divide that by the number of petals, 3 petals, now I know that my spacing angle is going to be 2 pi over 3. So for that exact reason, excuse me, that tells us that if my first petal is here at pi over 6, rotate around my second petal is going to be at 5 pi over 6. My third petal, continuing that rotation, is going to be at 3 pi over 2. And now we know where our petals are going to live. And again, this is all based on my spacing angle of 2 pi over 3. Last thing before I sketch this in, we know since this is a sine curve that I should be symmetric to theta equals pi over 2, and it absolutely appears that that's going to be the case. So next with our zeros, we know that if we had to go through this hassle to figure out where the first petal is going, where the payoff comes in is that with a sine curve, that our first zero will be at 0. We'll talk about the others here in a couple of minutes. But another way that we could have found the number of zeros is that if this is a sine curve, I begin my sketch on the pole. So right here, I have 1, 0, 2, 3, and 4. So again, another way that we could have gotten to the fact that we have 4 zeros, just realized that I hadn't made that sketch yet. But back to the specific zeros, anytime we have a sine rose curve, first zero is going to be at 0, no questions asked. And then that's where we get back to this spacing angle. We know that if the petals are spaced out evenly, so are the zeros. So that 2 pi over 3, that's what I'm going to continue to add here. So my first 0 is at 0. My second now is at 2 pi over 3. My third, if I add 2 pi over 3 again, I'm at 4 pi over 3. And we claim to have 4 zeros, so I have to absolutely showcase that we have 4 zeros. So at 2 pi over 3, we get 6 pi over 3, or 2 pi. And here are my zeros. Now the significant points we've already plotted them over there. And I know that we've kind of verbally spoken through, but I know that all my significant points, so they're going to have a max R value of 4. So looking something like this, we said that the first was going to be at 4 comma pi over 6, the second was 4 comma 5 pi over 6, and the final 4 comma 3 pi over 2. So I believe that we've identified where everything is going to go. Again, we had to handle this problem in a certain way because not only the fact that this was a Rose curve, but specifically this was a sine Rose curve. So in number 9, we have another Rose curve, but this time we're going to have a cosine. So you're going to notice that we're going to do a lot of the same math, but in slightly different orders and different scenarios, I guess, for lack of a better way of saying that. So again, we have a Rose curve. That's already been established. And looking, we could also further establish that A is equal to 5, N is equal to 2. This time, N is an even number. So I can't just say, all right, N is 2, so 2 petals. We have to double this. So if N equals 2, 2 times 2 is 4 petals. All right, the max R value, it's basically just restating what A is equivalent to, so 5. The number of zeros, again, we said that the number of, for a cosine curve, that the number of petals is equivalent to the number of zeros, so we should have 4 petals. Again, when we actually draw our sketch, we should prove, I suppose, for lack of a better way of saying that, that's still going to be the case. So now again, we talked about trade-off before with the sine problem. You might remember we had to do a significant amount of work, again, with this little formula, n theta is equal to pi over 2. We had to do that work to figure out where the first petal is. No such work has to be done on this cosine problem. We know that the first the first petal, is going to live on the polar axis. So all that we have to do is hit the max R value of 5, so counting out 1, 2, 3, 4, 5, and there's the first petal. Okay? If you're wondering why it works out this way, just remember where we have to be symmetric. And we have to be symmetric to the polar axis, so the first point lives on the polar axis. That's just the way it goes. So, just like before, let me identify some of this. Let's see, we said that the first petal, anytime it's a cosine problem, it's going to be at theta equals 0. That's great. But then now, I can't spell. So now we have to figure out our spacing. So spacing angle, if you recall, we're going to take a full circle of 2 pi and now divide that by the number of petals, which we've already claimed that there are 4 petals. So cleaning that up, my spacing angle is going to be pi over 2. So what that means for us is that if my first petal is at 0 plus pi over 2, I have my second petal, plus pi over 2, I have my third petal, plus pi over 2, I have my fourth petal, plus pi over 2, we're right back to where we started. So when we draw in the curve, remember for any cosine problem, we begin our sketch on the polar axis. So that's at this point right here. This is where I'm actually going to draw from. So we're still counting how many times we cross through the pole. So it's starting here. We're going to draw through. We count 1, 2, 3, 4, and we're back to where we started. So we already claimed that there should be 4 zeros, and the way we made that sketch just further solidified that, yep, we had 4 zeros. So now actually finding the zeros, again, specifically the first 0, that's where the hassle is going to come in with a cosine problem. And surprise, surprise, we use the same equation. N theta is equal to pi over 2. So we, a while ago, claimed that n was 2, if I'm remembering correctly, yes. So in saying that 2 theta is equal to pi over 2, multiplying both sides times 1/2, we can say that theta is equal to pi over 4. So we found our first 0. Again, it is located, sorry, we're doing this blue. We said that it's located at pi over 4. And then now we also know that the spacing of those angles is going to follow the same spacing of my petals. So I now need to just add pi over 2 in order to get 3 pi over 4 plus pi over 2, I get 5 pi over 4 plus pi over 2, I get 7 pi over 4. We said that there were 4 zeros, so we know that we can stop. Last thing we need to do is identify our significant points, and basically it's just writing up where they're located. So we have 4 of them, all of which have an R value, max R value of 5. So we started at 5, 0, we went to 5 pi over 2, 5 pi, 5, 3 pi over 2. So we have our significant points, our zeros, our max R value, the shape was a rose curve with 4 petals. And that's what it looks like. We have one more problem to go.